So here I have a rational function that I'm going to use to illustrate a removable discontinuity. As a matter of fact, that's the only type of discontinuity that this particular function has. That's why I've chosen it for this example. But certainly, as we move into some other functions, they can have both removable and non-removable discontinuities, and I'm sure you'll come across several examples of that. But this one here, just for now, removable only. So the first thing I want to do here is I want to go ahead and find the values that make the denominator equal to 0. That's going to be my points of discontinuity where the function is undefined. Kind of connecting it back to my previous video about just finding values where it's undefined. So let's go ahead and factor everything here. I'm going to go ahead and factor the numerator and the denominator. I can already look at the denominator and I know where it's going to be undefined. If I said x minus 4 equal to 0 and solve, I'm going to get 4 for that. So let's look at what happens when we factor the numerator as well. So we factored the numerator here, and I have this trinomial x squared minus 3x minus 4. I know I can split up my x squared term as x, and I need numbers that multiply to negative 4 that also happen to add up to negative 3. That would be negative 4 and positive 1. Negative 4 times 1 is negative 4. Negative 4 plus 1 is negative 3. So I've factored my numerator. Again, review the videos on factoring if you need to see a few of those examples to get back into the swing of things there. On the bottom, you just have this x minus 4. I'm going to go ahead and throw parentheses around it just so that you're identifying it as a common factor with something in the numerator. I want to make them look a little bit more similar there. So, connecting it to my previous example video, the values that make this undefined would be where the denominator is equal to 0. So if I set that equal to 0, x minus 4 equals 0, I would get x equals 4. That's where this function is undefined. So now the question is that a removable or a non-removable discontinuity where x is 4? Well, as a matter of fact, if you look at your function and the factor that created that point of discontinuity cancels out completely right there from the denominator, that would exhibit a removable discontinuity. I always like to say it removed itself entirely from the denominator when I tried to simplify from that. If the factor had still existed in the denominator, then that would not be a removable discontinuity. But when the factor cancels out completely like that from the denominator, we're talking about something that's removable. So we just found the value that made this undefined and said that this is a removable discontinuity where x equals 4 because that factor canceled out completely from the denominator. With that. So now what does that mean for the graph? Well, a removable discontinuity actually is represented by a hole in the graph. So when you look at the graph of the function, on the function where x equals 4, if you go up to where the corresponding y value where that would be on the graph, you won't actually see the graph being continuous there. You'll see a little open circle there designating a hole in the graph. If you wanted to actually figure out where the hole in the graph was located, if you were trying to make the actual graph of this function, you would take the simplified version of the function, which now, after we've canceled that out, we're just left with y equals x plus 1, and you would plug 4 into that. So I would have y equals, plugging this value in, I have 4 plus 1, I get y equals 5 to go along with that, meaning that there will be a hole where the x value is 4 and the y coordinate is 5. With that. So that's how you find the location of the hole in the graph with that. A removable discontinuity represents a hole in the graph of the function. We call it a removable discontinuity because we could very quickly redefine the function by just saying, well, let's let the function equal 5 at that point. We could create a piecewise function if you're familiar with that. Non-removable discontinuities are called non-removable because you can't do that. You can't just redefine a certain point like that. I liken it to filling in a pothole on the road. There's a little hole in the graph, there's a little hole in the road, I can just go out and throw a little bit of stuff in there and fill it in. That's what we removed the problem then. So that's why we call it a removable discontinuity, if you want a kind of a simple everyday connection example.